In roughly 450 BC, a religious order in southern Italy drowned one of their own members at sea. His crime was a geometry proof. In 1918, a German mathematician died of a heart attack in a psychiatric hospital, alone during the last winter of the First World War. He had been hospitalized on and off for decades, and the thing that broke him was a proof about infinity. In 1978, the greatest logician since Aristotle starved to death in Princeton, New Jersey, weighing 65 pounds because he could not trust the world enough to eat. He had proven that mathematics cannot know itself. 3 deaths, 3 centuries, 3 completely different branches of mathematics, and they are the same story, the same wound, opened in 500 BC by a man who measured the diagonal of a square, and it has not closed. It has widened through Cantor and Kronecker, through Gödel and Turing, through a number called omega that is provably unknowable, all the way to a 2019 paper by a physicist in Geneva asking whether the numbers in the equations of physics actually exist. Tonight, you are going to see where that wound leads. And by the end, the number line you were taught in school, that clean, smooth, fully understood object, is going to look like something else entirely. Get comfortable. Subscribe or join if you haven't. If you want more of this, longer explorations across physics, math, deep history, and the parts of science that don't get talked about enough, that's what the Patreon is for. Stay to the end of this one, because where the math lands in the last 20 minutes is something I genuinely did not expect when I started reading the papers. Let's ease into it. Pick up a ruler, draw a square, any size, it does not matter. Now measure the diagonal. That length, the distance from one corner to the opposite corner, is a number that cannot be written down. Not approximately cannot, not practically cannot. Fundamentally, mathematically, provably cannot. It will not end. It will not repeat. Not if you converted every atom in the observable universe into ink and wrote digits until the heat death of the cosmos. The square root of 2 is a number that exists. You can draw it. You can hold it between 2 points on a piece of paper, but it cannot be expressed as a ratio of any 2 whole numbers, no matter how large. And in roughly 450 BC, on a ship somewhere in the Mediterranean, a man was drowned for proving this was true. His name was Hippasus of Metapontum. He was a member of the Pythagorean brotherhood, a religious and political order that controlled large parts of southern Italy, and he had committed the one unforgivable sin. He had found a crack in the foundation of reality, not the metaphorical foundation, the actual foundation, the Pythagorean doctrine that held the cosmos together, the doctrine that said everything, music, astronomy, the structure of matter, the human soul, was built from ratios of whole numbers. Hippasus proved that this was wrong. He proved that the most elementary shape in geometry, the square, contains within it a quantity that no ratio can reach, and the brotherhood killed him for it. That is the version of the story you may have heard. A man was murdered over a math proof. It is usually told as a quirky footnote in the history of mathematics, a 2-paragraph anecdote about irrational Greeks and irrational numbers. And that framing is a lie by omission, because the crisis Hippasus uncovered in 450 BC was never resolved. It was buried, worked around, papered over for 2,000 years, and when mathematicians finally confronted it head-on in the 1870s, what they found was not a solution. What they found was that the problem was infinitely worse than Hippasus could have imagined. The crack in the foundation did not close. It widened, and it has been widening ever since, through Cantor and Kronecker, through Gödel and Turing, through Chaitin and Gisin, and it is open right now, at this moment, in the foundations of mathematics and physics. The number line you were taught in school, that clean, orderly continuum stretching from negative infinity to positive infinity, is hiding something so deeply strange that most of the mathematicians who understand it would rather not talk about what it means. I spent an unreasonable amount of time reading about this, and what I found is that the story of the square root of 2 is not really about the square root of 2. It is about whether mathematics, the language we use to describe reality, is capable of containing reality. And the answer, as of right now, is no. Provably, formally, rigorously, no. That is not my interpretation. That is what the theorems say, published, proved, peer-reviewed, and so far universally accepted by every mathematician who has checked the work. The language of reality cannot describe itself. The map cannot contain the territory. And the gap between what mathematics can say and what mathematics is, the gap that Hippasus stumbled into 25 centuries ago, turns out to be not a crack, but a chasm, and the chasm turns out to contain almost everything. But that is not even the disturbing part. The disturbing part is what that means for you, for the physical universe you live in, for the atoms you are made of, for the light hitting your eyes right now. Because if the mathematics is incomplete, and it is, and if almost every number on the number line is beyond the reach of computation, and it is, then what exactly are the equations of physics written in? What language are the laws of nature expressed in? And if that language is broken, what does that say about the laws? To understand why Hippasus had to die, you first need to understand what the Pythagoreans actually believed. Not the sanitized textbook version, the real thing, because the Pythagoreans were not a school of philosophy. They were a cult. The word is not an exaggeration or a metaphor. They were a secretive religious order with initiation rites, dietary restrictions, vows of silence, a doctrine of reincarnation, political ambitions, and a willingness to use violence against members who broke the rules. Pythagoras himself, born on the island of Samos around 570 BC, had fled the tyranny of Polycrates and arrived in the Greek colony of Croton in southern Italy around 530 BC. Within a generation, his followers effectively controlled the city. New initiates were called akausmatikoi, which translates roughly as listeners. They were required to observe 5 years of total silence before they were permitted to speak in meetings or see the face of Pythagoras himself. 5 years. Imagine that. 5 years of listening and not being allowed to ask a single question, not being allowed to contribute a single thought, simply absorbing the doctrine in silence. After the silence period, if they were judged worthy, they were promoted to mathematikoi and given access to the inner teachings. Members swore oaths on the Tetractys, a triangular arrangement of 10 dots in 4 rows, 1, 2, 3, 4, which they considered the most sacred object in existence. The oath, as preserved by Iamblichus, ran something like, "By him who transmitted to our generation the Tetractys, source and root of everlasting nature." They were swearing by the number 10. They were swearing by arithmetic. The Tetractys was not a symbol of mathematics. It was, for these people, the mathematical structure of the divine. They believed the soul transmigrated between bodies after death, that certain animals might contain the reborn souls of former humans, and that eating beans was forbidden. Ancient sources disagree on the reason for the bean prohibition. Aristotle suggested it was because beans resemble human testicles. Diogenes Laertius reported that Pythagoras believed beans contained the souls of the dead. Other sources suggest a more practical explanation involving flatulence at sacred rituals. Whatever the reason, It was taken seriously enough that when Pythagoreans were later hunted down during the anti-Pythagorean revolts, multiple ancient accounts describe members choosing death rather than fleeing through a bean field. Iamblichus tells the story of a group of Pythagoreans fleeing from attackers who arrived at the edge of a bean field and stopped. They would not enter it. They stood there and were killed. This is important context, not because it is colorful, but because it tells you something about the intensity of the commitment. These were people whose relationship to their doctrine was not academic, it was sacred. And the doctrine at the center of everything, the belief that organized their cosmology, their ethics, their politics, their music, their astronomy, and their understanding of the soul, was 4 words long. All is number. Aristotle preserves the doctrine in the Metaphysics, written around 350 BC. The Pythagoreans devoted themselves to mathematics. They were the first to advance this study, and having been brought up in it, they thought its principles were the principles of all things. He continues, since of these principles numbers are by nature the first, and in numbers they seem to see many resemblances to the things that exist and come into being, they suppose the elements of numbers to be the elements of all things, and the whole heaven to be a musical scale and a number. The whole heaven to be a musical scale and a number. That is not a loose philosophical metaphor. The Pythagoreans meant it literally, and they had evidence. Pythagoras, or someone in his circle, had made one of the most remarkable discoveries in intellectual history. They had found that musical harmony, the difference between a consonant chord and an ugly noise, could be reduced to the ratios of small whole numbers. Pluck a string, now press it at exactly half its length, and pluck again. The note is 1 octave higher. The ratio is 2 to 1. Press it 2/3 the length. The note is a perfect fifth above the original. Ratio 3 to 2. Press at 3/4. A perfect fourth, 4 to 3. The most beautiful sounds the human ear can perceive correspond to the simplest possible numerical relationships. Now consider how that must have felt in the 5th century BC. You have just discovered that beauty itself is mathematical, that the subjective experience of harmony maps perfectly onto the objective relationships between integers. The universe, it seems, is not chaos. It is not arbitrary. It is built from small whole numbers in beautiful proportions. And if music is ratio, then why not everything else? The distances between planets, the Pythagoreans believed, corresponded to musical intervals. This was the harmonia, turn sphären, the music of the spheres, a celestial harmony produced by the orbital motions of the heavenly bodies, inaudible to human ears, only because we have heard it since birth and no longer notice it. The seasons were ratio, the elements were ratio. The human soul itself was a ratio, a tuning, a harmonia. The entire cosmos was a symphony of whole numbers in proportion. And then someone looked at a square. I need to be precise about what happened here, because the mathematics is not difficult, but the philosophical devastation is total. Take a square with sides of length 1, just 1 unit, a tile on a floor, the most ordinary shape in the world. Now draw the diagonal. By the Pythagorean theorem, which the Pythagoreans certainly knew even if they did not originate it, the length of that diagonal is the square root of 1 squared plus 1 squared, which is the square root of 2. Now try to express the square root of 2 as a fraction. Try to find any 2 whole numbers, call them p and q, such that p divided by q equals the square root of 2 exactly. Not approximately, exactly. You cannot do it. It is not that nobody has found the right numbers yet. It is that a proof exists, and it is devastating in its simplicity, showing that no such numbers can exist. Here is the argument. Suppose the square root of 2 equals p over q, where p and q are whole numbers with no common factors. Square both sides. 2 equals p squared over q squared. Therefore, p squared equals 2 times q squared. This means p squared is even. If p squared is even, then p itself must be even, because the square of an odd number is always odd. So p equals 2 times some other whole number. Call it k. Substitute back. 2k squared equals 2q squared, which simplifies to 2k squared equals 2q squared. So q squared equals 2k squared, which means q squared is even, which means q is even. And there it is. Both p and q are even. But we started by assuming they have no common factors. Both cannot be even if they share no common factors. The assumption that the square root of 2 can be written as a fraction leads to a contradiction. Therefore, the assumption is false. Therefore, no fraction equals the square root of 2. The proof is complete. It is airtight. And it means that the diagonal of the simplest shape in geometry is a length that is not a ratio. Not a ratio of any two numbers, no matter how large. For you and me, sitting here in the 21st century, this is a moderately interesting mathematical fact. We learn it in school, we nod, we move on. We have already absorbed the concept of irrational numbers into our number system. They sit on the number line between the fractions, and we use them without thinking about it. But for the Pythagoreans, this result was not a moderately interesting fact. It was the end of the world. I want to stay on this moment longer than a textbook would, because I think the human weight of it gets lost. Imagine you are a member of the Pythagorean inner circle. You have spent 5 years in silence, studying, demonstrating your worthiness. You have been admitted to the rank of mathematicoi. You have sworn an oath on the Tetractys. You have organized your entire understanding of reality around the conviction that whole numbers and their ratios are the fundamental substance of the cosmos. This is not an intellectual position for you. It is closer to a religious revelation. You have heard the perfect fifth, the ratio 3:2, ringing on a stretched string, and you have understood with the full force of mystical experience that the universe sings in whole numbers. Your politics are based on this. Your astronomy is based on this. Your theory of the soul is based on this. And then a fellow member, someone who swore the same oath, demonstrates rigorously, irrefutably, using the brotherhood's own methods, that the most ordinary shape in the world contains a length that violates the foundational axiom of your entire belief system. Not a complicated shape, not some exotic construction. A square, a tile on the floor of the meeting house where you debate mathematics. The diagonal of that tile is proof that your cosmology is broken. What do you do? What do any of us do when the evidence contradicts the foundation? The history of ideas suggests that the first response is almost always the same. You attack the person who brought the evidence. Think about what it means if your entire cosmology, your religion, your politics, your understanding of the soul, your theory of music, your theory of the planets, your theory of everything, is built on the claim that all is number, where number means ratios of whole numbers, and then someone proves that the most basic shape in geometry contains a length that is not a ratio. It means your cosmology has a hole in it that no ratio can fill. It means geometry and arithmetic, the two pillars of Greek mathematics, contradict each other. It means the universe is not, after all, a symphony of whole numbers in proportion. It means something exists that your entire system says should not exist. And it exists in the most mundane place imaginable. A square, a tile on a floor. The Greeks had a word for these quantities. Actually, they had two. The first was allegon, which is usually translated as irrational, but literally means without ratio or without word or unspeakable. The second was ariton, which means inexpressible or forbidden to utter. These are not dry, technical terms. They are words of horror, the thing that cannot be spoken, the thing that has no logos. In a philosophical tradition, where logos meant not just ratio and word, but also reason and the ordering principle of the cosmos, a quantity that was a logos was a quantity that existed outside reason itself. It was a flaw in the fabric of reality. And Hippasus found it, or at least the ancient sources say he did. I need to be honest about the history here because it matters. We do not have a first-hand account of what Hippasus proved or how he died. The earliest surviving references come from writers working more than 700 years after the events. Iamblichus, writing around 300 AD, gives multiple contradictory versions. In one account, Hippasus was expelled from the brotherhood for revealing the discovery of incommensurability to outsiders. In another, he was drowned at sea, and the drowning was attributed to divine punishment from the gods. In yet another version, the specific crime was not the square root of 2 at all, but the inscription of a dodecahedron inside a sphere. Pappus of Alexandria, writing in the 4th century AD, says only that an unnamed Pythagorean perished by drowning for revealing mathematical secrets. Proclus, in the 5th century, mentions the discovery of incommensurables, but does not name Hippasus specifically. Modern scholars Burckhardt, Knorr, von Fritz have spent decades trying to untangle the legend from the history. The consensus is that the story conflates several different events and possibly several different people. The proof of the irrationality of the square root of 2 probably dates closer to 450 BC than to Pythagoras' own lifetime, which ended around 495 BC. Whether Hippasus was the specific person who produced the proof is uncertain. Whether he was actually murdered is uncertain. But here is what is not uncertain. Something about this discovery was catastrophic enough that 700 years later, the cultural memory of it was still associated with death, divine punishment, and exile. Whatever actually happened, the Pythagorean tradition preserved the emotional truth, even if the historical details blurred. The discovery of irrational numbers was experienced as a trauma. The mathematical fact that the diagonal of a square is incommensurable with its side was, for the people who first confronted it, not a curiosity. It was a catastrophe, and the response was not to absorb the discovery and adjust the doctrine. The response was to suppress the discovery and destroy the discoverer. And that pattern, that specific pattern of a reality-disrupting mathematical discovery being met with suppression and personal destruction, was going to repeat itself over and over. For the next 2,500 years, the Pythagorean brotherhood did not survive long after the crisis. The internal rupture over incommensurability was only one factor. The political backlash was far more violent. Around 509 BC, a wealthy aristocrat named Cylon, who had been refused admission to the brotherhood, led an uprising in Croton. According to Iamblichus, the rebels surrounded a meeting house, possibly the home of the wrestler Milo of Croton, and set it on fire while the Pythagoreans were inside. Some accounts say that members threw themselves into the flames rather than flee. Polybius records a second wave of anti-Pythagorean violence around 450 BC across the Greek cities of southern Italy, Croton, Metapontum, Tarentum, in which most remaining Pythagoreans were killed. Only a handful of members survived. The tradition continued underground, but the political and institutional power was gone. What did survive, though, was the problem. The mathematical problem, and the Greek response to it reveals something extraordinary about how human beings deal with truths they cannot accept. They did not solve it. They did not extend their concept of number to include irrationals. They did not rewrite their foundations. What they did instead was build the most elaborate avoidance strategy in the history of mathematics, a strategy so successful that it lasted nearly 2,000 years. They gave up on number. Eudoxus of Cnidus, born around 400 BC, was a student of Archytas, who was himself a Pythagorean. Eudoxus developed what is now called the theory of proportions, preserved in Book 5 of Euclid's Elements, and it is a masterpiece of mathematical ingenuity aimed directly at the problem of incommensurability. The key is definition 5 of Book 5. Two pairs of magnitudes are in the same ratio if for every possible pair of positive whole numbers m and n, when you multiply the first magnitude by m and compare it to the second multiplied by n, the ordering is the same for both pairs. The definition is deliberately, precisely, carefully constructed to allow you to reason about ratios of incommensurable magnitudes without ever calling them numbers. You can compare ratios. You can prove ratios are equal. You can build an entire geometry on proportions, and you never have to confront the fact that the quantity you are working with cannot be expressed as a fraction. This is the mathematical equivalent of building a bridge over an abyss and then pretending the abyss is not there. Greek mathematics, after Hippasus, divided into two separate domains. Arithmetic dealt with numbers, meaning positive whole numbers and their ratios. Geometry dealt with magnitudes, meaning lengths, areas, and volumes. The two domains were kept carefully apart. A length could have a ratio to another length, but that ratio was not a number unless it happened to be commensurable. The entire classification system of Euclid Book 10, which is the longest and most technically demanding book of the elements, is devoted to cataloging 13 different types of incommensurable lines. 13 types. That is how much mathematical machinery was required to manage a problem they refused to solve by simply saying, irrational numbers exist. This separation lasted from roughly 400 BC to 1872 AD. Nearly 23 centuries. The number line was not made whole for over 2,000 years. Think about that for a moment. The fundamental object of mathematics, the continuum, the line on which all of calculus and analysis are built, was conceptually broken for longer than any civilization in history has lasted. The Roman Empire rose and fell. The Middle Ages passed. The Renaissance came and went. The scientific revolution rewrote physics. Newton and Leibniz invented calculus in the 1670s, built an entire mathematical framework on the assumption that the continuum is smooth and complete, and never rigorously defined what an irrational number actually is. They used the number line. They assumed it worked. And underneath the calculus, underneath the integrals and derivatives and infinite series that transformed physics and engineering, the old Pythagorean wound was still there, unhealed, papered over with 2,000 years of increasingly sophisticated avoidance. When Richard Dedekind, a German mathematician teaching at the Swiss Federal Polytechnic in Zurich, finally confronted the problem head-on, the circumstances were almost absurdly mundane. He was preparing a lecture on the basics of analysis for first-year students. He needed to prove rigorously that a continuous, monotonically increasing function that is bounded above has a least upper bound, a bread and butter theorem, the foundation of calculus. And he realized with what he later described as genuine discomfort that he could not prove it because he did not actually have a rigorous definition of what a real number is. The concept of irrational number, the concept that Hippasus had forced into existence 23 centuries earlier, had never been formally defined. Mathematicians had been using irrational numbers for centuries, the way engineers use a bridge. It holds, it works. Nobody asks whether the pillars reach bedrock. Dedekind wrote that the idea came to him on November 24th, 1858. His construction is now called the Dedekind cut. Every real number is defined by a partition of the rational numbers into two sets, one containing all rationals less than the number, and one containing all rationals greater. An irrational number like the square root of 2 is the cut that separates all rationals whose square is less than 2 from all rationals whose square is greater than 2. The number itself is the cut, the gap, the boundary between the two sets. It is defined not by what it is, but by where it sits, by the hole it fills in the rational number line. He did not publish it for 14 years. The paper, Stetigkeit und irrationale Zahlen, Continuity and Irrational Numbers, appeared in 1872, the same year that Georg Cantor independently constructed the real numbers through a different method, using Cauchy sequences of rational numbers. Between them, Dedekind and Cantor finally gave irrational numbers a rigorous definition and a permanent home on the number line. I find it telling that Dedekind waited 14 years. He had solved the oldest oaken problem in the foundations of mathematics, and he put the manuscript in a drawer. He later said he had been unsure whether the construction would be accepted, whether the mathematical community was ready for a definition of real numbers that placed the irrationals on equal footing with the rationals, whether they were ready to say, officially, formally, that the square root of 2 is a number. 23 centuries after Hippasus, the hesitation was still there. And here is where you might expect the story to end. The problem was solved, the number line was unified, arithmetic and geometry were reconciled. 2,000 years of avoidance finally gave way to acceptance, and mathematics moved on. But that is not what happened, because the moment Cantor looked closely at the number line he had just completed, he found something that made the Pythagorean crisis look like a warm-up exercise. He found that the irrational numbers do not merely exist alongside the rationals. They overwhelm them, totally, absolutely, to a degree that the human mind genuinely struggles to process. And the story of what this discovery cost him is, if anything, worse than the story of Hippasus. Georg Cantor was born in St. Petersburg on March 3, 1845, the eldest of 6 children. His father, Georg Waldemar Cantor, was a successful merchant and devout Lutheran who wrote to his son constantly, urging him to pursue a career in engineering or the natural sciences, something practical, something that would bring financial security. The young Cantor was drawn irresistibly to mathematics. His father eventually relented, and Cantor studied at the University of Berlin under Kronecker, Weierstrass, and Kummer. He earned his doctorate in 1867 with a thesis on number theory. In 1869, he accepted a position at the University of Halle, which was considered a respectable but second-tier institution. He applied repeatedly for positions at Berlin, the most prestigious mathematics department in Germany. He never received one. The reasons were primarily political, and the politics had a name: Leopold Kronecker. Kronecker was one of the most powerful mathematicians in Germany, a professor at the University of Berlin, and until his death on December 29, 1891, the gatekeeper of what was considered legitimate mathematics. Kronecker was a brilliant mathematician himself, a contributor to number theory and algebra, and by all accounts, a formidable presence in the German mathematical world. He believed with religious intensity that only the natural numbers and their finite constructions were real. God made the integers, he reportedly said. All else is the work of man. He regarded infinite sets, irrational numbers, and anything that could not be constructed in a finite number of steps as illegitimate. And when his former student, Georg Cantor, began publishing papers that not only used infinite sets but proved that infinity comes in different sizes, Kronecker set out to destroy him. I want to be careful here because the relationship between Cantor and Kronecker has been mythologized in ways that oversimplify a complex history. Kronecker was not a villain in a melodrama. He was a serious mathematician with a coherent philosophical position, the finitist or constructivist position, which holds that mathematical objects are legitimate only if they can be explicitly constructed in a finite number of steps. This position is not absurd. It has modern adherents. Kronecker's objection to Cantor's work was not random cruelty. It was the collision of two incompatible visions of what mathematics is. But the collision was real, and the damage was real, and the damage fell entirely on Cantor. The first major result came in 1874, when Cantor published a paper in Crell's journal, proving that the real numbers are uncountable. The set of all real numbers, the complete number line, cannot be put into a one-to-one correspondence with the natural numbers. There are too many of them. Not just more, incomparably, immeasurably, qualitatively more. The proof was elegant, but the implications were explosive. Because if the reals are uncountable and the rationals are countable, then the irrationals, the numbers that caused all the trouble in the first place, must be the source of the uncountability. There are so many more irrationals than rationals that the rationals essentially vanish inside them. But the full force of this did not arrive until 1891, when Cantor presented his diagonal argument at the inaugural meeting of the Deutsche Mathematiker Vereinigung in Halle, a meeting Cantor himself chaired because he had founded the society. The argument is so simple and so devastating that I need to walk through it precisely. Suppose someone claims to have a complete list of all real numbers between 0 and 1. Every single one, arranged in some order. The first number on the list has its decimal expansion, an infinite string of digits. The second number has its expansion. The third has its, and so on, for every natural number. Cantor's move is this: construct a new number by looking at the first digit of the first number and choosing a different digit. Then look at the second digit of the second number and choose a different digit. Then the third digit of the third number, a different digit. Continue forever. The number you have constructed differs from the first number in at least its first decimal place, from the second number in at least its second decimal place, from the third in its third, and so on. It differs from every number on the list. Therefore, it is not on the list. Therefore, the list was incomplete. But you assumed the list was complete. Contradiction. No list of real numbers, no enumeration, no matter how clever, can capture them all. The reals are uncountable. The proof fits in a single paragraph, and it shattered the foundations of mathematics. Now here is the part that should make you pause. The rational numbers, every fraction you have ever written, every ratio of whole numbers, every number the Pythagoreans would have recognized, form a countable set. You can list them. It takes some cleverness, but it can be done. The irrationals, on the other hand, are uncountable. And in measure theory, the branch of mathematics that deals with the size of sets, the rational numbers have Lebesgue measure 0 on the real number line. If you pick a real number at random from any interval, the probability that it is rational is exactly 0. Not approximately 0. Exactly 0. The rational numbers, every number you have ever used in daily life, occupy precisely none of the number line. They are an infinitesimally thin film on an ocean that is almost entirely irrational. I need to pause here because I think the weight of this gets lost in the abstraction. Imagine the number line as a road stretching from 0 to 1. Every point on that road is a real number. Now paint every rational point on that road blue and every irrational point red. If you could somehow zoom out and see the entire road at once, you would see nothing but red. The blue points are there, infinitely many of them, densely packed. Between any two of them, there are infinitely many more, and yet they take up no space at all. The road is, in every meaningful measure theoretic sense, entirely red, entirely irrational. The numbers we understand, the numbers we can write as fractions, the numbers the Pythagoreans worshipped, are not just a minority on the number line. They are, in the precise mathematical sense, nothing. Measure 0. They have no width. They occupy no room. They are ghosts. I want to give you another way to feel this. Imagine throwing a dart at the number line between 0 and 1. A perfectly accurate dart landing on a perfectly precise point. The probability that you hit a rational number is 0, not small. 0. The probability that you hit an irrational number is 1. Certainty. If you threw the dart an infinite number of times, the expected number of times you would hit a rational number is 0. Infinity times 0. The rationals are so sparse, so negligibly thin in the measure-theoretic topology of the real line, that infinite repetition does not help. They cannot be hit. They are there, but they are not, in any meaningful probabilistic sense, present. Every number you were taught in school lives in this set of measure 0. Every fraction, every decimal you have ever calculated, every answer to every math problem you have ever solved, all of it. Ghosts on a red road. And here is the connection back to Hippasus. The Pythagoreans believed all is number, meaning all is ratio. Hippasus showed that one specific length, the diagonal of the unit square, is not a ratio. That was bad enough to get him killed. But what Cantor showed, 2,300 years later, is that Hippasus had only found the first drop of an ocean. The irrationals are not exceptions to the rule of rationality. Rationality is the exception. The universe of numbers is almost entirely irrational. The Pythagorean worldview was not slightly wrong. It was infinitely wrong. The ratios they worshipped are an infinitesimally thin residue on a number line they could not have imagined. Kronecker understood the implications, which is precisely why he tried to stop Cantor. Not because the mathematics was wrong, because the mathematics was right, and the implications were intolerable for anyone who believed, as Kronecker did, that mathematics should be grounded in finite constructions. The campaign against Cantor was not a single dramatic confrontation. It was a slow, grinding, institutional destruction. Kronecker delayed the publication of Cantor's 1874 paper. He blocked Cantor from receiving an appointment at Berlin. He publicly mocked Cantor's work. Arthur Schoenflies, writing in 1927, reported that Kronecker referred to Cantor as a Verführer der Jugend, a corrupter of youth, and a scientific charlatan. I should note that Dauben, in his authoritative 1979 biography of Cantor, treats these as Schoenflies' paraphrases of Kronecker's stance, rather than verbatim quotations. What is documented, without dispute, is the editorial obstruction and the career sabotage. Henri Poincaré, the most famous mathematician in France, described Cantor's transfinite numbers as a grave mathematical malady, a perverse pathological illness that would one day be cured. First, it was impossible. Then when someone did it, it was trivial. The one thing it could never be was important. That pattern, again. Cantor suffered his first major depressive episode in May of 1884. The records from the Halle-Nerven Clinic list the diagnosis as cyclic, manic depression. He was hospitalized repeatedly from 1890 onward. Between breakdowns, he continued to work, but with increasing desperation, he became convinced that his transfinite numbers had been revealed to him directly by God. In a letter to the Swedish mathematician Gösta Mittag-Leffler, dated December 23, 1883, Cantor wrote, "I am only an instrument of a higher power that will continue to work long after me, just as it revealed itself thousands of years ago to Euclid and Archimedes." In a letter to the Franciscan theologian Ignatius Gyler, dated October 13, 1895, he wrote, "All these particular modes of the transfinite exist from eternity as ideas in the divine intellect. A man who proved that infinity comes in sizes, that the number line is almost entirely beyond rational comprehension, believed that the proof had been given to him by God, and the mathematical establishment treated him as though he had lost his mind. The irony is almost too precise to bear. The man who saw further into the nature of infinity than any human being before him was told by the people who could not follow where he went that what he was seeing was not real, that it was a symptom, that the infinite was pathological." David Hilbert, to his credit, disagreed. In 1926, Hilbert declared, "No one shall expel us from the paradise that Cantor has created." It was a noble sentiment, but it came decades too late for Cantor. Cantor died on January 6, 1918, of a heart attack in the Halle Sanatorium during the final winter of the First World War. He was 72. His wife Vally had died the previous year. He was alone. His conjecture, the continuum hypothesis, the question of whether there exists an infinity strictly between the countable and the continuum, remained unresolved. It would stay that way. Not temporarily, permanently. I need to stop here and show you something. Because if the Hippasus story and the Cantor story were isolated incidents, you could dismiss them as coincidences. A man killed over a number in ancient Greece, and a man driven to madness over infinity in 19th century Germany. Interesting, but unrelated. But they are not unrelated. They are instances of a pattern that has repeated itself with disturbing regularity across the history of science. And once you see it, you cannot unsee it. And it changes how you think about the relationship between human institutions and uncomfortable truths. Giordano Bruno was a Dominican friar, a philosopher, a mathematician, and a cosmologist. In the 1580s, he proposed that the universe is infinite, that the stars are distant suns, that those suns are orbited by planets, and that the universe has no center. He proposed that matter is composed of irreducible minima, a version of atomism. He proposed that the cosmos is alive, animate, that the divine does not stand apart from nature, but pervades it. He was arrested by the Inquisition in Venice in 1592. He was imprisoned for 7 years. On February 17, 1600, he was led to the Campo de' Fiori in Rome. Stripped naked, his tongue clamped in a metal gag so he could not speak, and burned alive. The official charges were heresy. Scholars have debated for centuries whether the cosmological claims were central to his condemnation or merely incidental. Alberto Martinez, in his 2018 book Burned Alive, published by the University of Chicago Press, argues that Bruno's belief in infinite worlds and an animate cosmos was not peripheral to the charges. It was the core of them. The Church did not simply disagree with Bruno. The Church could not allow a universe that needed no center, no boundary, no hierarchy. An infinite cosmos threatens the architecture of authority. Ludwig Boltzmann was born in Vienna on February 20th, 1844. He was one of the founders of statistical mechanics, the branch of physics that explains how the macroscopic properties of matter, temperature, pressure, entropy, emerge from the behavior of enormous numbers of atoms. His core claim was that atoms are real, not useful fictions for calculation, real, physical objects, and that the second law of thermodynamics, the law that entropy always increases, is not a fundamental law, but a statistical one, a consequence of the overwhelming probability that a system will move toward its most probable configuration. This sounds uncontroversial now. In the 1890s, it was considered by many leading physicists to be somewhere between speculative and absurd. Ernst Mach, the most influential philosopher of science in the German-speaking world, rejected the physical reality of atoms entirely. He regarded them as metaphysical constructs, useful for calculation, but not to be taken as describing real entities. Wilhelm Ostwald, the leading physical chemist of the era, argued that energy, not matter, was the fundamental substance of reality, and that the atomic hypothesis was unnecessary. Boltzmann spent the last 2 decades of his life defending the physical reality of atoms against attacks from Mach, Ostwald, and their followers. The attacks were public, relentless, and often personal. On September 5, 1906, while on vacation with his wife and daughter at the seaside resort of Duino, near Trieste, Boltzmann hanged himself. He was 62. His daughter found the body. The reasons for his suicide were complex, involving chronic depression, deteriorating eyesight, and exhaustion. But his biographers, including Carlo Cercignani, consistently identify the sustained institutional rejection of his work as a major contributing factor. The supreme irony is that within 3 years of his death, Jean Perrin's experiments on Brownian motion provided definitive physical evidence for the reality of atoms. By 1909, the debate was over. Boltzmann was right, and Boltzmann was dead. Here is the pattern. Hippasus proved that certain quantities are not ratios. The Pythagoreans killed him. Cantor proved that infinity comes in sizes, and that the irrationals swamp the rationals. Kronecker destroyed his career. Boltzmann argued that atoms are real. Mach and Ostwald drove him to despair. Bruno argued that the universe is infinite. The Inquisition burned him alive. I am not claiming these are identical cases. The mechanisms differ. The centuries differ. The specific ideas differ. What does not differ is the shape. An individual discovers or proposes something that dissolves a boundary the existing power structure needs to remain intact. The boundary between the rational and the irrational. The boundary between the finite and the infinite. The boundary between the continuous and the discrete. The boundary between the knowable and the unknowable. And the institution, whether it is a religious cult, a church, a university, or a scientific establishment, responds not by examining the evidence, but by destroying the person. And here is the part that should make you angry. You were educated inside these institutions. The version of mathematics and physics you received in school was shaped by the same institutional forces that suppressed Hippasus, burned Bruno, broke Cantor, and let Boltzmann die, not by conspiracy, not by deliberate malice, by the much subtler and more pervasive mechanism of what is considered appropriate to teach, appropriate to discuss, appropriate to think about out loud. The questions that were too uncomfortable were simply omitted from the curriculum, not answered and put to rest. Omitted, left out. The textbook went from Pythagoras to Euclid to Descartes to Newton, and never mentioned that the number line spent 23 centuries broken, that infinity comes in sizes, that mathematics cannot prove its own consistency, or that almost every number that exists is beyond the reach of computation. Those facts were available, published, peer-reviewed, and you were never told. That is not a gap in education. That is a shape, and it is the same shape every time. Before we get to why the continuum hypothesis matters, I need to tell you about a different kind of impossibility, because Cantor's work revealed that the number line contains overwhelmingly more irrationals than rationals. What came next was worse. What came next was the proof that mathematics, the entire system, the whole edifice of logic and proof and deduction that humanity has built over 25 centuries, has a permanent blind spot, a hole that cannot be patched, cannot be worked around, cannot be fixed, because it is not a bug, it is a feature. And the man who proved it starved himself to death in a hospital in Princeton, New Jersey, weighing 29 kilograms. Kurt Gödel was born on April 28, 1906, in Brunn, the capital of Moravia, then part of the Austro-Hungarian Empire. He was a preternaturally gifted child, known to his family as Der Herr Warum, Mr. Why, for his relentless questioning. He studied at the University of Vienna, and by the age of 23, had obtained a result that destroyed the most ambitious project in the history of mathematics. The project was David Hilbert's. Hilbert, born in Königsberg in 1862, was the most influential mathematician of the early 20th century. In 1900, at the International Congress of Mathematicians in Paris, he had presented a list of 23 unsolved problems that he believed would shape the future of mathematics. The first problem on the list was Cantor's continuum hypothesis. The second was the consistency of arithmetic. Hilbert believed both could be solved. He believed all mathematical problems could be solved. Wir müssen wissen. Wir werden wissen, he said in a famous radio address in Königsberg in 1930. We must know. We will know. That address was delivered on September 8th, one day after Gödel's announcement. Hilbert did not know yet. He was declaring victory on the day the war was already lost. Hilbert's program was to formalize all of mathematics into a set of axioms, like Euclid's, but more rigorous, and then prove within the system that the system was complete, meaning every true statement could be proved, and consistent, meaning no contradiction could ever be derived. This was not a minor technical project. It was the mathematical equivalent of building a fortress around all human knowledge, a system that could prove its own trustworthiness. It was the most ambitious intellectual project in human history, and Gödel killed it in a single paper. On September 7th, 1930, at a conference on epistemology in Königsberg, the 24-year-old Gödel stood up and announced, almost casually, during a roundtable discussion on the second day, that the project was impossible. The conference had been organized to discuss the foundations of mathematics. Hilbert himself had spoken the day before. The atmosphere was optimistic. Hilbert's program was the dominant research agenda. Mathematics was going to be placed on a foundation of absolute certainty. And then Gödel, barely out of his doctoral studies, mentioned, almost as an aside, that he had found a way to construct true but unprovable sentences in any consistent formal system. The room did not react. Almost nobody understood what he had said. The discussion moved on. Only one person in the audience grasped the significance. John von Neumann, then 26, approached Gödel afterward and asked for details. Von Neumann went home, worked furiously, and within weeks had independently derived the second incompleteness theorem as a corollary. He then learned that Gödel had already done so. Von Neumann later said that Gödel's result was the most important thing to happen in logic since Aristotle. He also said that once he understood the proof, he gave up his own work in mathematical logic entirely. If Gödel was right, and he was, then the program von Neumann had been pursuing was dead. There was no use continuing. The full paper, titled On Formally Undecidable Propositions of Principia Mathematica and Related Systems, was received by the journal Monatshefte für Mathematik on November 17, 1930, and published in 1931. Gödel was 25 years old. He had just destroyed the most ambitious intellectual project of the 20th century, and most of the mathematical world did not yet realize it. Hilbert, when he finally understood the result, was reportedly furious, then depressed. His program, the dream of a self-verifying mathematics, the dream of building a fortress around all human knowledge, was not merely unfinished. It was unfinishable. Gödel had not shown that the foundation was too hard to build. He had shown that the foundation does not exist. The first incompleteness theorem states that any consistent formal system capable of expressing basic arithmetic contains true statements that cannot be proved within the system. Read that again. It does not say, we have not found the proofs yet. It says the proofs do not exist. There are mathematical truths that are true, genuinely true, and no amount of logical deduction from the axioms will ever reach them. The system has blind spots that are intrinsic to its structure. The second incompleteness theorem is worse. It states that no such system can prove its own consistency. The fortress Hilbert wanted to build, a system that proves itself trustworthy, is not merely unbuilt. It is unbuildable. Mathematics cannot verify its own foundations. It cannot look in the mirror and confirm that what it sees is not contradictory. Not because we are not clever enough, because Gödel proved it is logically impossible. Only one person in the audience at Königsberg that day understood what Gödel had done. John von Neumann, who immediately went home and independently derived the second incompleteness theorem as a corollary before learning that Gödel had already done so. Von Neumann later said that Gödel's result was the most important thing to happen in logic since Aristotle. I want to stop here and connect this back to the thread, because the chain of implications is unbroken, and it runs in one direction. Hippasus proved that the square root of 2 is not a ratio. This meant that geometry contains quantities that arithmetic cannot reach. The response was suppression and murder. 23 centuries later, Cantor proved that these unreachable quantities, the irrationals, overwhelm the rationals so completely that the rationals have measure 0. The response was institutional destruction and madness. And then Gödel proved something even deeper. Not just that there are numbers we cannot express as ratios, not just that there are more unreachable numbers than reachable ones, but that there are truths within mathematics itself that mathematics cannot reach at all. The system cannot see its own limits. It cannot prove its own safety. The pattern is the same every time. Someone discovers that the knowable is smaller than we thought. The unknowable is larger, and the boundary between them is a wall, not a horizon. And every time, the person who discovers this is destroyed for it. Gödel drew the most radical possible conclusion from his own theorems. In his 1951 Gibbs lecture at Brown University, he stated, "Either mathematics is incompletable in this sense, that its evident axioms can never be comprised in a finite rule. That is to say, the human mind, even within the realm of pure mathematics, infinitely surpasses the powers of any finite machine. Or else there exist absolutely unsolvable Diophantine problems. He believed the first option. He believed the mind is not a machine. He believed his theorems proved that consciousness transcends computation. And he believed that mathematical objects are real, not useful fictions, not mental constructs, real. In a 1964 supplement to his essay, What is Cantor's Continuum Problem?, Gödel wrote, "Despite their remoteness from sense experience, we do have something like a perception also of the objects of set theory, as is seen from the fact that the axioms force themselves upon us as being true. I don't see any reason why we should have less confidence in this kind of perception, that is, in mathematical intuition, than in sense perception." And in his 1944 essay on Russell's mathematical logic, it seems to me that the assumption of such objects is quite as legitimate as the assumption of physical bodies, and there is quite as much reason to believe in their existence. Think about what that means. A man who proved that mathematics has permanent blind spots, that every formal system is necessarily incomplete, also believed that the mathematical objects beyond the blind spots are real, objectively existing things that the mind can perceive through something like intuition. He was not a mystic. He was arguably the greatest logician since Aristotle. And he was saying that the numbers are there, even the ones we cannot prove, even the ones we cannot reach. He spent the last decades of his life working on a proof of the existence of God using modal logic, not as a whimsical exercise, as a serious logical project. The same man who destroyed Hilbert's dream of a self-verifying mathematics tried, with the same tools, to prove the existence of a necessary being. The ontological argument, formalized in the notation of mathematical logic, he showed it to only a few colleagues and never published it during his lifetime. It appeared posthumously in 1970 in his collected works. Whether the proof is valid remains debated. That he attempted it at all tells you something about the kind of mind that stares into the incompleteness of formal systems and concludes, not that reality is unknowable, but that reality exceeds any system we build to describe it. For Gödel, the limits of mathematics were not evidence of emptiness beyond the limits. They were evidence of fullness, of a mathematical reality so vast and so real that no finite axiom system could capture more than a fragment of it. This matters. It matters because of what came next. Because the question Gödel could not answer, the question that haunted Cantor into the asylum and tormented Hilbert into stubborn denial, was about to be resolved, and the resolution was worse than any of them feared. The question of whether there is an infinity between the countable and the continuum. The question Cantor could not answer. The question that may have contributed to his breakdown. The first problem on Hilbert's famous list. Here is what happened to it. In 1940, Gödel proved that the continuum hypothesis cannot be disproved from the standard axioms of set theory. The Zermelo-Fraenkel axioms with the axiom of choice, commonly called ZFC. If those axioms are consistent, and every mathematician assumes they are, then you cannot derive a contradiction from adding the continuum hypothesis to them. Gödel published this as a monograph titled The Consistency of the Continuum Hypothesis through Princeton University Press. 23 years later, in 1963, a young mathematician named Paul Cohen at Stanford University proved the opposite direction, using a technique he invented called forcing, a method so original that it earned him the Fields Medal in 1966. Cohen showed that the continuum hypothesis cannot be proved from ZFC either. His paper appeared in the Proceedings of the National Academy of Sciences, Volume 50, pages 1143 to 1148. Together, the two results mean this: the continuum hypothesis is independent of the axioms. It is neither provable nor disprovable. It is not that we have not found the proof. The proof cannot exist. The gap between the smallest infinity and the continuum is, in the deepest sense, available to mathematics, unknowable from within mathematics. Gödel himself wrote to Cohen in June of 1963, calling the result the greatest advance in the foundations of set theory since its axiomatization. Think about what this means. Cantor's dying question, the question that tormented him through decades of hospitalization, the first problem on Hilbert's list, the question of how many infinities sit between the integers and the real numbers, is unanswerable, not unsolved, unanswerable. Mathematics contains a question about its most fundamental object, the number line, that it cannot resolve. There could be no infinities between the countable and the continuum. There could be one, there could be infinitely many. All options are consistent with the axioms. The number line, the thing you draw with a ruler, the thing we use to measure the world, has a structural ambiguity at the level of its infinite architecture that mathematics is powerless to resolve. Cantor broke his mind trying to answer this question, and the answer is that mathematics breaks before the question does. The man who proved mathematics has blind spots watched another man prove that one of the most important questions in mathematics lives inside the blind spot, and the blind spot is permanent. I want you to sit with this for a moment, because the implications are stacking. Hippasus showed that the number line contains unreachable quantities. Cantor showed that those quantities overwhelm the reachable ones. Gödel showed that the system we use to study the number line has permanent gaps in what it can know. And then Cohen showed that one of the most fundamental questions about the number line falls directly into that gap. Each discovery is worse than the last, and each discoverer paid for it. Gödel's end is one of the saddest stories in the history of science. He fled Austria in 1940, taking a circuitous route through the Soviet Union and Japan to reach the United States, and joined the Institute for Advanced Study in Princeton. His closest friend there was Albert Einstein. The two walked together to campus nearly every day, an odd pair, Einstein gregarious and rumpled, Gödel thin and meticulous, wrapped in a heavy overcoat, even in mild weather, already showing signs of the hypochondria that would define his later years. Einstein once told the economist Oscar Morgenstern that he went to the Institute every day only for the privilege of walking home with Gödel. When Einstein died on April 18, 1955, Gödel lost the one person at Princeton who understood what he was thinking. He became increasingly isolated. In 1947, when Gödel applied for American citizenship, Einstein and Morgenstern accompanied him to the citizenship hearing. Gödel, who had been studying the U.S. Constitution obsessively, told Einstein on the way to the hearing that he had found a logical inconsistency in the Constitution that could allow the United States to be legally converted into a dictatorship. Einstein and Morgenstern spent the car ride desperately trying to convince him not to mention this to the judge. Gödel mentioned it anyway. The judge, who happened to have emigrated from Europe himself, changed the subject quickly and granted the citizenship. It is a funny story. It is also a window into a mind that could not stop following logical implications to their conclusions, even when the conclusions were socially catastrophic. The paranoia deepened over the decades. In 1936, Back in Vienna, his friend and mentor Moritz Schlick, the founder of the Vienna Circle, was shot and killed on the steps of the university by a former student named Johann Nelberg. Nelberg had stalked Schlick for years, obsessed with a female student he believed Schlick had influenced against him. The murder was political as well as personal. The Nazis celebrated Nelberg's action, and the Austrian press published editorials suggesting that Schlick, who was Jewish, had provoked his own murder through his philosophy. The event devastated Gödel and confirmed, in his mind, that the world was a place of arbitrary violence. He became convinced that he was being poisoned. He ate only food prepared by his wife, Adele, a former nightclub dancer whom he had married in 1938 over his family's objections. She was the one constant in his life, the one person he trusted enough to eat the food she cooked. When Adele suffered a stroke in late 1977 and was hospitalized for 6 months, Gödel stopped eating. He was admitted to Princeton Hospital on December 29, 1977. He died on January 14, 1978. The death certificate listed the cause as malnutrition and inanition caused by personality disturbance. He weighed 29 kilograms, 65 pounds, the greatest logician since Aristotle, the man who proved that mathematics cannot know itself, starved to death because he could not trust the world enough to eat, a man who perceived mathematical objects as real, who believed the mind transcends computation, who proved the limits of every formal system, could not perceive a world safe enough to accept food from anyone but his wife. I want to make sure the weight of the biographical thread is clear before we continue, because it is not decoration, it is evidence. Hippasus, drowned or exiled, the exact method lost to history, but the violence remembered for 700 years. Cantor, hospitalized repeatedly from 1899 until his death in the Halle Sanatorium in 1918. Gödel, starved to death in Princeton in 1978. Boltzmann, hanged at Duino in 1906. These are not metaphors for the difficulty of mathematics. These are the actual physical consequences that fell on actual human bodies for the crime of looking too closely at the foundations of the number system. Each one found a deeper layer of the same problem. Each one paid with their mind or their life. And I keep coming back to the fact that you were probably never told any of this. Not in school, not in any math class, not in any popular science book aimed at general audiences. You were given the number line as a finished product, a smooth continuum from negative infinity to positive infinity, with rational and irrational numbers peacefully coexisting. The 2,500-year war that produced that number line was simply not mentioned. The bodies were buried. The institutional violence was omitted. And the fact that the war is not over, that the foundations are still unsettled, that the questions are still open, was presented as though it were resolved long ago. That is not an oversight. That is the invisible scandal, and it is happening right now in every high school and university mathematics department in the world. And still, we have not reached the bottom. Because after Gödel, after incompleteness, after the continuum hypothesis was shown to be undecidable, a mathematician named Gregory Chaitin went further. In 1975, Chaitin defined a number that makes the entire discussion collapse to its most concentrated and disturbing form. It is called omega, the halting probability. It is defined as the probability that a randomly chosen computer program running on a universal Turing machine with a specific prefix-free coding will eventually stop rather than run forever. Omega is a real number. It sits somewhere between 0 and 1. Every digit is well defined. It is not vague not approximate, not philosophical. It is a specific, precise, definite, real number. And Chaitin proved that it cannot be computed. No algorithm can produce its digits, not approximately, not eventually, not with infinite time and infinite resources. The digits of omega are provably beyond the reach of computation. Furthermore, omega is algorithmically random. It has no pattern, no compression, no shortcut. Every digit is maximally unpredictable given all the previous digits. It is randomness incarnate, a number that exists, that is completely defined, and that is completely unknowable. Khaloud, Dineen, and Xu, in a paper in Experimental Mathematics in 2002, managed to compute the first 64 bits of one specific omega. Beyond that, the digits are forever inaccessible. I want to be precise about what forever means here, because people sometimes hear cannot be computed and think it means cannot be computed with current technology, or cannot be computed in a reasonable amount of time. That is not what it means. Chaitin's proof is absolute. There is no future technology, no quantum computer, no civilization at the end of the universe with resources we cannot imagine that could compute the digits of omega. The impossibility is not practical. It is mathematical. It is of the same character as the proof that the square root of 2 cannot be expressed as a fraction. Not hard, not impractical, impossible. In the precise, logical, if you assume, otherwise you get a contradiction sense of the word. And omega is not special. That is the part I keep circling back to. Omega is not a freak. It is not an exotic curiosity at the edges of mathematics. It is typical. It is what most real numbers are like. The vast, overwhelming majority of real numbers are not only irrational, but uncomputable. They cannot be produced by any algorithm. They cannot be described by any formula. They cannot be specified by any finite string of symbols in any language. If you could somehow point at a random spot on the number line, the probability that you would land on a computable number is 0. Not approximately 0. Exactly 0. The computable numbers, like the rationals, have measure 0. They occupy no space. So consider the hierarchy. The natural numbers, 1, 2, 3, 4, are the skeleton. Minimal, discrete. The Pythagoreans worship them. The rationals, the fractions, fill in some of the gaps. They are dense on the number line. Between any two, there are infinitely many more. And yet they occupy no space. Measure 0. Then the algebraic numbers, the roots of polynomial equations with integer coefficients. Add the square root of 2, the cube root of 3, the golden ratio. Still countable. Still measure 0. Then the computable numbers, every number that any algorithm could ever produce, including pi, e, and every number any human or machine has ever calculated, or will ever calculate, still countable, still measure 0. And everything else, the overwhelming bulk of the number line, the ocean on which all of these vanishingly thin layers float, is uncomputable, unnameable, unreachable. Gregory Chaitin himself has written about the philosophical implications with unusual directness for a mathematician. He has described the set of computable reals as islands of structure in a sea of randomness, and has argued that mathematics, far from being the most certain form of human knowledge, is shot through with irreducible uncertainty. The number line, the object that mathematicians have studied for millennia, the foundation of calculus and analysis and physics, is almost entirely terra incognita, not unexplored territory waiting for future explorers. Permanently, provably, irrevocably unknown territory. There is no map that could cover it. Not because the terrain is difficult, because the terrain is, in a rigorous mathematical sense, unmappable. Omega is not an anomaly. It is typical. This is the part that should genuinely unsettle you. The computable real numbers, the numbers that can be produced by some algorithm, some finite description, some formula, are countable. They form a set of measure zero on the real number line. Almost every real number is uncomputable. Not just irrational, not just transcendental, uncomputable, beyond the reach of any algorithm, any formula, any finite description in any language that has ever existed or will ever exist. The knowable numbers are nothing. Literally, measure, theoretically, nothing. The number line is almost entirely populated by quantities that no mind, no computer, no civilization, no matter how advanced, could ever specify. They exist. They are there. And they are permanently, provably, irrevocably out of reach. Do you see the shape of this now? Do you see what has been happening since 450 BC? Hippasus found one number that cannot be a ratio. The Pythagoreans said it should not exist and killed him. Cantor found that such numbers are almost everything. Kronecker said they should not exist and destroyed his career. Gödel found that mathematics itself has permanent limits on what it can know. Hilbert's program said those limits should not exist, and Chaitin found that almost every number lies beyond even the limits of computation. The pattern is the same every time. The unknowable is not a margin, not an edge case, not a curiosity. It is the ocean. And the knowable, everything we can name and calculate and write down, is a vanishingly thin film floating on the surface. Every time you punch a number into a calculator, every time you measure anything, every time a physicist writes an equation, you are working in that film. You have never left it. No human being has ever left it. No computer has ever left it. The entirety of human mathematics, the entirety of human computation, every number that has ever appeared on every screen and every page in the history of civilization lives in a set of measure zero, in nothing. And here is the part that I keep turning over in my mind. The computable numbers include everything you would think of as a real number. Pi, e, the square root of 2. Every algebraic number. Every number that any formula or algorithm could ever produce. These are the numbers with names, with definitions, with properties we can study. And they are, collectively, nothing. If the number line is a country, the computable numbers are not a city. They are not a village. They are not even a single point. They are a set of measure zero, a mathematical ghost town on an infinite continent that no mind will ever survey. Chaitin's omega is one resident of that continent, but it is the continent itself that should keep you awake. The infinite, teeming, dark interior of the number line that computation cannot reach and that no finite description can touch. It is there. It is most of what there is, and it is permanently, provably, irrevocably silent. And the equation that describes your heartbeat, the differential equation that models the electrical signal propagating through the sinoatrial node of your heart right now, uses the full real number continuum as its domain. Your heartbeat depends, mathematically, on a number line that is almost entirely inaccessible. The mathematical description of the most basic biological process in your body requires numbers that no mind will ever specify. Now, one last descent, because everything I have told you so far has been about mathematics, about numbers and proofs and formal systems. It has all been, in a sense, abstract. The question is whether any of this touches reality, physical reality, your reality. The answer is that it might, and the implications are staggering, and almost nobody is talking about it. Consider the fine structure constant, alpha. It is the number that governs the strength of the electromagnetic force. Every interaction between light and matter, every photon absorbed or emitted, every chemical bond in your body is controlled by this single dimensionless constant. It has been measured to extraordinary precision. The best current value, published in Nature in 2020 by Leo Morel, Zibin Yao, Pierre Clade, and Saida Guelati Khalifa at the Castres Brossel Laboratory in Paris, is 1 divided by 137.035, 999,206, with an uncertainty of 81 parts per trillion. That measurement was achieved using matter wave interferometry on rubidium atoms. Richard Feynman wrote about this number in QED, The Strange Theory of Light and Matter, published in 1985. It has been a mystery ever since it was discovered more than 50 years ago, and all good theoretical physicists put this number up on their wall and worry about it. It is one of the greatest damn mysteries of physics, a magic number that comes to us with no understanding by man. You might say the hand of God wrote that number, and we don't know how he pushed his pencil. Nobody knows where alpha comes from. Nobody knows why it has the value it has. Nobody knows whether it is rational or irrational. Nobody knows whether it is computable. After a century of trying, no one has been able to derive it from any combination of pi, e, the golden ratio, or any other known mathematical constant. Arthur Eddington spent years trying. He convinced himself alpha was exactly 1/136, then revised to 1/137, constructing increasingly baroque algebraic arguments that the physics community rejected. Wolfgang Pauli became obsessed with the number 137. When he was hospitalized with pancreatic cancer, his hospital room was number 137 at the Rockkreuz Hospital in Zurich. He reportedly told his assistant that he would not get out of that room alive. He was right. He died on December 15th, 1958, in room 137. Alpha appears in the equations as a brute fact about the universe, with no explanation. It is a number that governs the probability of every electromagnetic interaction in existence. Every time an electron absorbs a photon, every time a photon is emitted, every chemical reaction in your body, every nerve impulse in your brain, controlled by a number that we have measured to 12 significant figures but cannot explain at all. If its value was slightly different, if it were 1/138, instead of approximately 1/137, the nuclear resonance in carbon-12 that allows stars to synthesize carbon would not occur. No carbon, no organic chemistry, no DNA, no life. The number that holds your body together is a number we found, not derived, measured, not understood. And after nearly a century of the most intense theoretical effort in the history of physics, it remains exactly as mysterious as the day Sommerfeld first calculated it in 1916. The number that holds your body together, that makes light behave the way it does, that determines the size of atoms and the color of fire, is a number we cannot explain, cannot derive, and cannot even classify as rational or irrational. It sits there, in every equation of quantum electrodynamics, like a lock for which no key exists. You are probably not thinking about the fine structure constant right now, but it is operating in your body at this moment, governing every electromagnetic interaction between every atom you are made of. The screen you are looking at emits photons whose energy is determined by alpha. The retinal molecules in your eyes absorb those photons at rates determined by alpha. The neural signals carrying this information to your brain propagate along axons whose biochemistry is governed by alpha. The thought you are having right now about whether to believe what I am telling you is itself a pattern of electromagnetic interactions, every one of which is controlled by a number we have measured but cannot explain. And nobody knows whether that number is rational. Nobody knows whether it is computable. If it is uncomputable, then a number that governs the behavior of every photon in the universe is a number that no algorithm could ever produce. A number from the dark ocean, not from the thin film. A number that, according to Chaitin's framework, contains infinite irreducible information, infinite randomness, a number that cannot be compressed or summarized or derived from anything simpler than itself. If you want to feel the vertigo, that is where you feel it, not in the abstraction of set theory, not in the formalism of incompleteness theorems. Here, in the light touching your eyes right now, governed by a number that might be permanently unknowable. And here is where it gets worse. In 2018, Nicolas Gisin, a physicist at the University of Geneva and one of the founders of quantum information theory, published a paper on the arXiv titled Indeterminism in Physics, Classical Chaos and Bohmian Mechanics. Are real numbers really real? It later appeared in Incompleteness in 2019, and a follow-up commentary appeared in Nature Physics in 2020. The argument is disarmingly simple and profoundly unsettling. Classical physics, Newtonian mechanics, assumes that physical quantities like position and velocity are real numbers, not just approximately real numbers, exactly real numbers with infinitely many digits of precision, each digit fully defined. This seems like a harmless mathematical convenience. Everyone uses real numbers. Every equation in classical physics is written in terms of them. The position of a planet, the velocity of a billiard ball, the temperature of a gas, all modeled as real numbers. It is so deeply embedded in the practice of physics that questioning it feels almost absurd. But Gisin questioned it, and his argument is hard to dismiss. A single real number, if it is irrational and uncomputable, contains infinite information. Its digits cannot be compressed, cannot be summarized, cannot be produced by any finite description, not because the description has not been found, because it cannot exist. Gisin pointed out that if classical physics assigns a real number to the position of a particle, then a single particle at a single moment in time contains more information than every book ever written, every computer ever built, and every thought ever conceived, combined. An infinite amount of information packed into a single point in space. Where is this information stored? How does the universe process it? If a billiard ball's velocity is a real number with infinitely many defined digits, and the outcome of a collision depends on those digits, then the physics of billiard balls requires the universe to perform computations on infinite strings. Every bouncing ball, every falling apple, every orbiting planet would need to carry inside its physical state an infinite amount of precise information. Not approximately infinite, exactly infinite. That is not a philosophical quibble. It is a physical absurdity. Or at least, it is a claim so extraordinary that it should make you deeply uncomfortable, because you are left with exactly two options, and neither of them is reassuring. Option 1. The universe genuinely contains infinite information at every point. Every particle carries in its exact position and velocity a real number with infinitely many digits, all of which are physically real, all of which influence the future evolution of the system. This means that the information content of even the simplest physical system, a single particle in a box, is infinite. It means that classical determinism, the idea that the future is determined by the present state, requires the present state to contain infinite data. It means that the universe is, in a very precise sense, infinitely complex at every point, at every moment. Option 2. The real number continuum is a mathematical fiction that does not correspond to physical reality. The number line we use to describe the universe might not be in the universe at all. Physical quantities might not be real numbers. They might be something else, something with only finite precision, something that does not require infinite information to specify. In this case, the smooth, continuous number line of mathematics is an idealization, a useful approximation that works spectacularly well for predictions but does not describe what is actually there. Gisin proposed replacing classical real numbers with intuitionist mathematics, a framework developed by the Dutch mathematician L.E.J. Brouwer in the early 20th century. In intuitionist mathematics, numbers are not completed objects with all their digits defined in advance. They are ongoing processes. A real number in Brouwer's framework is a sequence of better and better rational approximations, produced one at a time, and at any finite moment, the number is specified only to the precision that has been produced so far. The remaining digits are not merely unknown. They do not yet exist. They are created, not discovered, as the process unfolds. In this framework, something remarkable happens to classical physics. The equations are the same, the predictions are the same, but the interpretation changes radically. Classical mechanics becomes genuinely indeterministic, not because of quantum effects, but because the initial conditions are never specified to infinite precision. And without infinite precision, the future is not uniquely determined. The indeterminism is built into the mathematics itself, and it mirrors, eerily, the indeterminism of quantum mechanics. Gisin wrote in the Nature Physics commentary that classical physics and quantum physics may be two sides of the same coin when formulated without the real number continuum. This is a minority position. I need to be clear about that. The standard practice in physics, the practice that has produced spectacularly accurate predictions for centuries, uses real-valued mathematics without philosophical anxiety. The equations work. The predictions match experiments to extraordinary precision. Quantum electrodynamics, formulated in terms of real and complex numbers, agrees with experiment to 12 decimal places. No one disputes the utility, but the equations work is the same thing the Pythagoreans said about their ratios. The ratios worked. The musical intervals were correct. The harmonic proportions were accurate. The predictions matched observation. And then someone measured the diagonal of a square. The debate Gisin opened is live and unresolved. There are physicists on both sides. Tim Palmer at Oxford has argued along similar lines, proposing that the undecidability of real number arithmetic is connected to the apparent indeterminism of quantum mechanics. Christian Kalud and Carl Svozil have published work connecting Chaitin's incomputability results to quantum randomness. The question of whether physical reality requires the full real number continuum or whether something smaller and more structured would suffice is an active area of research. It is not settled. It is not consensus. But the fact that the question is even being asked, the fact that a respected physicist at a major university published a peer-reviewed paper asking whether real numbers are physically real, is itself a kind of Hippasus moment. It is someone standing inside the tradition, holding up a result from within the system's own rules and saying, "This does not add up. The foundation has a crack in it, and the crack has been there since the beginning." Here is the shape of the story when you pull all of it together. 2,500 years ago, someone proved that the most basic shape in geometry contains a quantity that the existing number system cannot express. The response was murder. The mathematical tradition then spent 23 centuries avoiding the problem rather than solving it. When it was finally confronted in the 1870s, the mathematicians who confronted it discovered that the problem was not a gap, but an abyss. The irrational numbers are not the exception, they are everything. The rational numbers are measure zero. They are nothing. The man who discovered this was hospitalized and died in a sanatorium. Then another mathematician proved that the system itself, the logic, the axioms, the deductive framework, has permanent holes. Truths it cannot reach. Consistency it cannot verify. He starved to death in a hospital, weighing 65 pounds. Then a third mathematician proved that almost every number on the number line is not merely irrational, but uncomputable, beyond the reach of any algorithm, any description, any mind. The knowable numbers are an infinitesimally thin residue on an ocean of permanent unknowability. And now a physicist is asking whether the ocean is even real, whether the numbers we cannot compute exist in any physical sense, whether the continuum is a mathematical ghost story we have been telling ourselves for millennia. And nobody is talking about it, not in the way it deserves, not in the way that conveys what it actually means for you, for me, for anyone who has ever assumed that the mathematics underlying our description of reality is solid ground. This is published mathematics. This is published physics. The incompleteness theorems are in every logic textbook. The uncountability of the reals is in every analysis textbook. The measure zero status of the rationals and the computables is in every measure theory textbook. Chaitin's omega is in the research literature. Gisin's paper is in a peer-reviewed philosophy of physics journal. None of this is hidden. None of this is fringe. None of this is controversial within the relevant fields. And yet, when you learned about the number line in school, you were shown a smooth, continuous, fully comprehensible object. When you learned about irrational numbers, you were told they are just numbers that cannot be expressed as fractions, as though this were a minor technical distinction, like the difference between hardwood and softwood. Nobody told you that the irrationals overwhelm the rationals so completely that the rationals have measure zero. Nobody told you that almost every number on that smooth, comprehensible line is uncomputable. Nobody told you that the central question about the line's infinite structure is provably unanswerable. Nobody told you that the man who discovered the hierarchy of infinities died in an asylum, or that the man who proved mathematics is incomplete starved to death, or that the community that first encountered irrational numbers responded with murder. All of that was available. All of it was true, and it was quietly, systematically not taught. Not because it was disproven, because it was too uncomfortable to include in a curriculum designed to make mathematics feel safe. I want to take this to the personal level now, because I promised earlier that the implications touch you directly, and they do. Think about what you use numbers for: your bank account, your mortgage rate, your body temperature, your blood pressure, the GPS coordinates of your house, the speed limit on the highway. Every quantitative fact about your life, every measurement, every calculation, every data point is a rational number, a fraction, a ratio. The numbers you use are, exclusively, the numbers that the Pythagoreans would have recognized. You have never used an irrational number in your life. You have never even specified one. You have used approximations of irrational numbers, 3.1416 for pi, 1.414 for the square root of 2, but the actual irrational number, the infinite, non-repeating decimal expansion, has never appeared in any calculation you have ever performed. And now consider that these numbers, the ones you use, the ones every human being and every computer has ever used, occupy exactly 0% of the number line. You live your entire quantitative life in a set of measure zero, an infinitesimally thin film, and the mathematics that describes your world, the calculus, the differential equations, the physics, is built on the full real number continuum, on the vast ocean of uncomputable numbers that you cannot specify and that no finite process can reach. The equations require those numbers. The existence and uniqueness theorems of differential equations depend on the completeness of the reals. The convergence of Fourier series, the spectral theory of quantum mechanics, the mathematical infrastructure of modern physics is built on a foundation that is almost entirely invisible to us. We use the surface film. The equations use the ocean. This is not a metaphor. This is a measure-theoretic fact about the relative size of the computable and the uncomputable on the real number line. And if Gisin is right, if the real numbers are not physically real, then the mathematical infrastructure of physics is built on something that does not exist in the physical universe it describes. The map is not the territory. The map is drawn on paper that the territory does not contain. If he is wrong, if the real numbers are physically real, then every point in space carries infinite information. Every particle encodes an uncomputable number in its exact position, and the physical universe is infinitely more complex at every point than any finite mind or computer could ever process. The universe is not just stranger than we suppose. It is stranger than we can suppose, to borrow Haldane's phrase. And the strangeness is not in the exotic phenomena of black holes and quantum entanglement. It is in the number line, in the diagonal of a square, in the gap between 1 and 2, that the Pythagoreans tried to pretend was not there. Hippasus, Cantor, Gödel, Chaitin, Gisin, 500 BC, 1874, 1931, 1975, 2019. The same discovery, made over and over, in different vocabularies, at different scales, with different tools, by people who mostly did not know they were continuing the same conversation. The discovery is always the same. The unknowable is larger than the knowable. The boundary between them is a wall, and the wall is getting closer, not farther, with every century of mathematical progress. The Pythagoreans carved the pentagram on their doors. It was their sacred symbol, the 5-pointed star inscribed in a regular pentagon. And here is the detail that makes the entire 2,500-year story feel less like a sequence of accidents and more like something mathematics has been trying to tell us from the beginning. If you draw a pentagram inside a regular pentagon, the diagonals intersect to form a smaller pentagon inside. And if you draw a pentagram inside that smaller pentagon, it forms an even smaller one. And so on. Endlessly, a recursive descent of pentagrams inside pentagons, inside pentagrams, shrinking toward a point, but never reaching it. And the ratio of the diagonal to the side of the pentagon is phi, the golden ratio, 1 plus the square root of 5 divided by 2, which is irrational. The process of trying to find a common measure between the diagonal and the side, the procedure called antipheresis, the reciprocal subtraction the Greeks used to test for commensurability, never terminates. It runs forever. The Pythagorean sacred symbol, the emblem of their doctrine that all is number, the sign they pressed into wax and carved into stone, contains within its own geometry the proof that their doctrine is wrong. The irrationality is not hiding in some exotic corner of mathematics. It is right there, inside the symbol itself, in every intersection of every line. They chose the wrong emblem. Or maybe they chose exactly the right one. Maybe the pentagram is a more honest representation of mathematical reality than any of them realized. A symbol that contains its own refutation. A structure that, the closer you look at it, the more it recedes into an infinite regress that no ratio can capture. I think about Cantor's letter to Mittag Leffler, written in December of 1883, in the years before the breakdowns consumed him. I am only an instrument of a higher power that will continue to work long after me, just as it revealed itself thousands of years ago to Euclid and Archimedes. He believed the mathematics was coming through him, not from him. He believed it was being revealed, not invented. And Gödel believed the same thing. Both men looked at the number line and perceived something real, something objective, something that exists independently of human minds. And both men were destroyed by the institutions that controlled the discourse about those objects. The numbers survived, the men did not. And here is the thought I still do not know how to sit with. If mathematical Platonism is correct, if the numbers are real, then the uncomputable numbers are real too. They are there, on the number line, occupying nearly all of it, permanently beyond the reach of any algorithm or description. They exist the way the square root of 2 exists, the way the diagonal of a square exists. But they are worse. The square root of 2 can at least be named, defined, approximated to arbitrary precision. An uncomputable number cannot even be singled out. You cannot point at it. You cannot describe it. You cannot distinguish it from its neighbors. It is there, but it is there in the way that dark matter is there, detectable in aggregate, invisible in particular. Gödel believed these objects are real and that the human mind can perceive them through mathematical intuition. He believed that what his theorems showed is not that mathematics is limited, but that the mathematical universe is so vast that no finite system can contain it. If he was right, then we are standing at the edge of a landscape so large that we cannot map it, cannot survey it, cannot even describe its boundaries. And the small piece we have mapped, the rationals, the computables, the provable truths, is an infinitesimal fraction of what is there. The ground under mathematics has been falling since Hippasus. It has never stopped. Every century, someone looks down and discovers the drop is further than the last person measured. Hippasus measured it in geometry. Cantor measured it in set theory. Gödel measured it in logic. Chaitin measured it in computation. Gisin is measuring it in physics. And every time, the answer is the same. The knowable portion of mathematical reality is smaller than you thought. The unknowable portion is larger, and the gap between them is not closing. Draw a square. Measure the diagonal. That length, right there, that specific distance from one corner to the other, is a quantity that took humanity 2,300 years to formally accept, and that opened a wound in the foundations of mathematics that has never healed and is not healing and shows no signs of healing. Every digit of the square root of 2 extends the decimal without repeating, without terminating, without pattern, into an expansion that is still going right now, in some sense, reaching for a precision that it will never arrive at. The Pythagoreans called it allegon, without word, without reason. They killed the man who found it, and the number is still there, on the diagonal of every square that has ever been drawn, on every tile, in every floor, in every building on earth, in the geometry of every crystal and every right angle in the physical universe. Patient, irrational, unspeakable, waiting for someone to explain what it means that the language of reality cannot speak its own name. 25 centuries later, we still cannot. And the silence is not an absence of knowledge. It is knowledge of an absence that runs deeper than any human system of symbols can reach, an absence that was always there, inside the simplest shape in geometry, written into the foundations of mathematics before the first number was ever named. The Pythagoreans heard the music of the spheres. They heard harmony in the ratios of small whole numbers, and in the diagonal of a square, in the emblem on their own doors. Reality was already singing a note they could not hear, a note outside every ratio, a note that will never resolve.